Hello everyone, in this problem, Koko the gorilla is eating some bananas. We are given an array representing piles of bananas, where each number in the array is the amount of bananas in each pile. We are also told how much time Koko has to eat all her bananas. Koko is going to be consuming the bananas at some fixed rate of X bananas per hour. However, Koko can only eat out of one pile per hour. This means that if there is a pile with one banana remaining, and Koko has chosen to eat at a rate of 10 bananas per hour, she's still only able to eat that one banana. Koko doesn't want to be rushed when eating bananas, but at the same time, Koko wants to finish all the bananas. Therefore, our goal is to find the lowest rate of consuming bananas that Koko can eat at, such that she's still able to finish all the bananas in the time limit. There is no limit to how many bananas Koko can eat per hour, and we are guaranteed that Koko will always have enough time to consume all her bananas. In other words, the number of hours will always be greater than or equal to the number of piles. There is also no predetermined order that Koko has to consume the bananas in. Let's go through a couple examples to better understand the problem. So if the piles array is 12, 8, 3, 4, and Koko has 7 hours to consume all the bananas, then our answer would be 4. If Koko eats at a rate of 4 bananas per hour, I've pasted out the progression of these 7 hours and how Koko would still be able to finish all her bananas. At any slower of a rate, say 3 bananas per hour, she would not be able to finish them all. Now in this example, we have the same pile, but rather than 7 hours, she only has 4 hours. Here, Koko is forced to eat at a rate of 12 bananas per hour, and I've pasted how that would look like over the 4 hours. Again, notice that Koko cannot consume from multiple piles within a single hour. So say in the second hour, when she was eating from the second pile, even though her rate is 12 and there are only 8 bananas in pile 2, she cannot move on to another pile and start eating from those. Okay, now that you have a better understanding of the problem, let's look at the brute force solution. The brute force solution is going to start from the slowest rate of 1 banana per hour. We then check if Koko can finish all the bananas at this rate. If she can't, then we increase the rate by 1 and try again. And we continue this until we find a rate where Koko finishes all the bananas. So this is where our solution starts. Our function is called eating bananas, and it takes in the piles variable as well as h, which is the number of hours Koko has. For every rate starting at 1 and ending at the max value of a pile, we call a function, which I'll get to in a moment, called canFinishEating. That function is going to determine if Koko can finish eating all the piles at a particular rate. If that is true, then we return the rate immediately. The reason our for loop stops at max piles is that if Koko eats the maximum bananas in a pile per hour, she's going to finish 1 pile per hour, which guarantees she will finish all the bananas. And remember from earlier that one of the constraints of the problem was that the hours Koko has to finish the bananas is always going to be greater than or equal to the number of piles. So for any given input, this is the fastest she's ever going to need to eat. We don't want Python to compute max piles every iteration, so let's save it as a variable. And ultimately, I have a return statement at the bottom here that returns null, but in theory, you should never reach this return statement. If we want to make this a bit cleaner and not return null, we can make the for loop only iterate to max piles minus 1 or max piles exclusive, and then return max piles instead of null if the algorithm does make it to the bottom. Now we have to get back to implementing the helper function canFinishEating. For this function, we have a variable called hours taken. This represents the hours it takes to consume all the bananas at a given rate. For every pile, the amount of hours it takes to finish consuming that pile is the size of the pile divided by the rate, and then the ceiling of that. We have to round up to the ceiling because Koko cannot move on to another pile within the same hour. Finally, if the time it takes to finish all the piles is less than or equal to the time limit h, then we return true because we can finish eating in time. Otherwise, we return false. You can clean that up to just return the condition itself. Let's look at the time and space complexity of this first solution. If we let m be the max number of bananas and n be the number of piles, then the time complexity is O of n times m. You can see this in the two nested for loops. In our main function, we have a for loop which can loop m times, and inside that for loop, we have the can finish eating function, which has its own for loop, which runs n times. For space, we aren't using any extra space, so that is just constant. Okay, now that you have seen the brute force solution, let's try and see how we can improve our solution. If we go back to the brute force solution, you'll notice that we started at a rate of 1 and incremented 1 by 1 up to the max value of a pile. Each increment costs us length of piles in terms of time complexity. And we are doing this until we find a rate at which Koko can finish eating the bananas. At this point, we should make the key realization that we are essentially trying to find a value in a sorted list. And binary search is going to be a faster way to do this as opposed to a linear traversal. So our strategy is going to look like this. We know the lower bound of the rate is 1, and the upper bound on the rate is the maximum of piles. So these are going to be the low and high of our binary search. This next part is basically just an implementation of binary search. We compute the mid and check and see if with that mid as the rate, can Koko finish eating the bananas? If she can, we move high to mid minus 1 because we want to aim for an even lower rate. We also need to record that this is the slowest rate we have discovered so far that Koko can eat at and still finish the bananas. If the if statement is false, which means at this mid rate Koko cannot finish eating, then we have to aim for a higher rate, so we move the low to mid plus 1. You should pretty clearly see how this is just binary search. The can finish eating function from the brute force solution is still going to come in handy, so let's copy that in. But now for our improved main function, we start off by initializing the low and high bounds of our binary search to 1 and the max of a pile respectively. We also start off the slowest rate at high. Next is pretty standard binary search. While low is less than or equal to high, we compute the mid by adding low to high and doing an integer division by 2. And then, this is the part I showed earlier, if for this mid rate, Koko can finish eating all the bananas, then we set the slowest rate to mid and we try going for an even slower rate. But if she cannot finish, then we go for a higher mid by setting the lower bound to mid plus 1. Finally, once the binary search is complete, we return the latest slowest rate. Okay, that is it for the implementation. Let's look at the time and space. Let's keep the same variables as the brute force solution, with m being the max amount of bananas in a pile and n being the number of piles. For time, first we have the binary search while loop, which is going to be logarithmic time complexity of the search space. The search space is 1 to max of piles, which is m. So binary search is O of log m. Within each iteration of the binary search though, we still call the can finish eating, which is O of n. So overall, our time complexity is n times log m. For space, we still aren't using any extra data structures, so our space stays constant. Alright, to recap, we went over a slower solution, which iterated through our search space linearly. Then we were able to improve our solution by making the realization that we could use binary search because our search space was essentially sorted. I hope this video helped you in understanding the problem. Thank you for watching and good luck on all your interviews.